it is my pleasure to introduce Professor Yifeng Yu. And hello, Yifeng.
Hi.
And would you like to tell us a little bit more about you and your academic path and your research?
Okay, so thanks for this opportunity. My name is Yifeng Yu. I'm a math professor at this department. Let me briefly introduce my research. So my research is on partial differential equation. So that means it's an equation that involves a partial derivative of unknown function. Let me just give you a very quick example. So that's considered one of the most important and fundamental example. It's called the Laplace equation. Okay, say you have a function u, which has two variables, x and y. And the Laplace equation says the u, second derivative with x, so u x x xy plus u y y xy equals 0. And this is called Laplace equation. So you see it's an equation that involves partial derivatives of u. And this is the one of the most important equation. Now, what is the meaning of that? So for the Laplace equation, it usually represents the quantity when it reaches equilibrium. For example, you think of the temperature, right? So if uxy represents the temperature at the location xy, say the temperature reaches equilibrium, that means it does not change. In other words, we say the heat conduction reaches balance. So how much it goes inside, how much it goes outside. And then if it reaches equilibrium, the temperature uxy, it's described by the equation uxx plus uyy equals 0. So that's the most basic one. Now, nowadays, PDE plays an essential role in the modeling of many applied things. For example, engineering. So you see PDE almost like everywhere in the modeling of problems in engineering, and also in physics, in biology, and also in finance. For example, the most well-known model in a hedge fund, which is the Black-Scholes model. That model is written in a PDE. And Black-Scholes, they discovered that model. They won the Nobel Prize. Okay. Yeah, so that is basically what I'm working on. Now, regarding PDE, there are two ways to do. One is we say, okay, you have PDE, you want to solve it, but in general, there's no formula to solve PDE. So what people do is, okay, we just use a computer to find a numerical solution. So that's one way to start a PDE. So when I say PDE, it's short for partial differential equation. And another way, it's what I'm doing is theoretical study. So our PDE, we study properties of solutions, like existence of solutions from a theoretical point of view. That means we prove things instead of doing numerical computation or numerical simulation.
Thank you, Yifeng. This seems like a very exciting area of research. When did you become interested in it?
Let me put it this way. So I think it's the process itself is interesting. When I went to Berkeley for my PhD program, first I wanted to study geometry. That's because there was a huge influence on geometry when I was in undergraduate study. But then when I went to Berkeley, I took various courses like algebra, geometry, and also a course of PDE. And then I find my natural tendency is I find a kind of like natural attachment to analysis to PDE. At the time I read a book, Partial Differential Equation by Lawrence Craig Evans. So this is, I think it's just a natural attachment. And I just fell in love with PDE and the many things associated with it. And from that point, I decided to work with Lawrence Craig Evans on PDE, and I just started my research career on PDE.
Wonderful. And I'm curious if our undergraduates are studying PDEs now, and if they find a job in applied math, are they likely to be using it for modeling?
Yeah, so that's for sure, because as I said, PDE nowadays is the most often used tools in modeling. In many things, when people say you want to study some continuous quantity, pressure, density, and temperature, as long as it's a continuous quantity, then always it's written in the form of PDE. Now, in the time of Newton, which we say is the era of so-called classical physics, then what people do is, instead of look at those continuous quantities, what people do is they just look at single particle, right? You say, okay, you have a single particle, you think of the sun or the earth, and you can view them as single particle, and they are moved on force. What you derived is ODE, because you just have one object. You look at the position at each moment with the time t. So that's why you get is an ODE. But in modern physics, so that's like after 19th century, people focus more on those continuous quantities, temperature, density, pressure, and those things. And then you usually got is a PDE. So for example, one of the most well-known PDE is Navier-Stokes equation. So that equation is like a cornerstone for basically everything that is related to fluid mechanics. When you are building airplane, when you're building cars, when you're building ships, you have to deal with the pressure, the fluid, like either the air or the water or all kind of those kind of things. Then eventually, the foundation, the equation that governs all those things, that's called Navier-Stokes equation. It's a PDE.
So you mentioned that you learned about PDEs as an undergraduate, right? And then you found it a fascinating field and decided to continue your studies in graduate school. So I have a question for you that maybe some of our students are wondering as well. When I decide to go to graduate school and maybe study applied math because it's so useful and so interesting, then am I really, can I only become a professor, or is that something that would also be useful in terms of an industry career? And why would I go to graduate school to study PDEs if I want to have a job in industry?
Okay, so first of all, myself is a theoretical mathematician. I'm not really applied mathematician, but what the question Alexander asked is very important. I often got the same question from undergrad students, and when they ask about their career paths. My answer is this. Okay, so why we want to go to grad school? So first of all, we already, it seems we already learned a lot of things in right? So we learned some undergraduate PDE, and we learned like important things. So when I tell people, I think that if you want to find, nowadays, if you want to find a good job, then the most relevant subjects is PDE, because as I said, PDE and ODE, of course, but PDE, those things, we combine to say it's differential equations because they appear everywhere if you are in terms of modeling. So you get to know it. And also they are, because they are not used alone in the modeling. Often they are combined with many other things like linear algebra and also probability, stochastic. Right? It's like today's in the machine learning, big data, and also in finance. Stochastic is often stochastic analysis with the probability is often combined with PDE. Now, so why we want to go to graduate school? That's because what you learned as an undergrad student often is not enough to handle high demanding jobs like in those, let's say, engineering, in finance, and in other applied science. So that's why I always encourage students, I say, if you want to do something which is more challenging and which requires a high skill, then you go to graduate school and get deep understanding of those important things. Again, it's like a PDE, a probability. So I think some of my colleagues, everyone know that the machine learning big data is very important, very hard, which is 100% true. I think some of my colleagues will cover that. I would just want to mention one thing. It's like a finance, right? Some of us are interested. I met quite a few students. They're interested in going to financial industry. So I will say that now, if you enter financial industry, what you want to do? If you want to do something which is highly specialized, you want to handle modeling things, then a very important thing is you cannot just say, oh, I have a software, I just implement the software and got what I want. That's far from being enough. What you to do? So that's why financial industry, they want to hire math PhD. The reason is they expect a math PhD to have the ability to understand the model and then has the ability to change the model according to their real situations. So to understand those models, as I said, for example, the model, Black-Scholes model, which is widely used in hedge fund, and all kind of options. All right. So for that, it's a PDE. You have a PDE, and also the PDE is derived through a stochastic process and stochastic, those kind of things. So when you go, those things will not be taught. Usually, it's not taught in undergraduate education. But if you go to a graduate study, then you will learn this. You have the opportunity to learn those kind of things, and you will really understand what are those things are introduced and how they are derived. And then you have the ability to really introduce like modified new models when you go to do things in the financial industry.
Thank you, Yifeng. And to just finish this little discussion that we are having, so you decided not to go to industry, right? You're a theoretical mathematician and you love the theory of PDEs. Can you share one thing? Why do you like that theory? Why did you naturally fall in love with the theory of PDEs when you studied it? Is there some aspects in particular that you enjoy compared to other areas of math?
So for me, I think it's one is I would say it's the natural tendency. It's like a personal taste. It's hard to explain like why you like this instead of that. So I think one bigger part is my personal taste. I just like theoretical things. I want to like prove things. So I understand like apply things very important and very interesting. But for me, somehow I just like more proving things. So that's one thing. Another thing is when I at graduate school, I met my PhD advisor, Lawrence Craig Evans. I mean, he is a great mathematician. I somehow just so admire him, and he had a huge influence on me. And then I think, I want to be a mathematician like him. And that's a big inspiration for me. So I decided to become a theoretical mathematician. So I would say combined together is, first of all, it's my personal taste. And second is a huge influence from someone I really admire.
Thank you very much for sharing your story. Thank you, Yifeng.
Okay. Thanks, Alexandra.